I've mostly been selling you on the idea of U substitution as a method for finding antiderivatives, for evaluating indefinite integrals. Let's think about what U substitution says just for definite integrals. So here's the setup. I've got the integral, x goes from a to b of some function f, not the derivative of f, just f, at g of x times g prime of x dx. Now, how could I approach a problem like this? Well, I can make a substitution. U equals g of x, so that du is g prime of x dx. And in that case, this integration problem becomes the integral of f of u, right? U is g of x, times this is du. But now I got to change the bounds of integration. When x is equal to a, u is g of a, and when x is equal to b, u is g of b. Assuming that those two integrals exist, to justify the equality of those two integrals, it's just the chain rule and the fundamental theorem of calculus. And yet this statement, the equality of this integral and this integral, that's just a statement about two definite integrals. I don't need to know the fundamental theorem of calculus in order to make this assertion. This raises a fascinating question. U substitution is making a claim about definite integrals, and yet the naive way to justify that claim goes through the fundamental theorem of calculus and the chain rule. Is it possible to see why the statement about U substitution for definite integrals should be true without resorting back to antidifferentiation? Well, to gain some insight into this, here's a random graph that I made of some function that's nearly constant, but the function I'm calling f. And this area in here is the integral from 1 to 10 of f of u du. Right? That's this area in here. Now I want to imagine what happens when I do the substitution. What happens when I replace u with x squared plus 1? And that changes du, right? That's that formula that we saw a moment ago. If I'm integrating f of u du, I could alternatively integrate f of g of x times du g prime of x dx. And I can imagine that in the graph. Transforming from the u coordinates to these x coordinates, well, the u coordinates are more stretched out, right? When x is 0, u is 1. When x is 1, u is 2. When x is 2, u is 5. And when x is 3, u is 10. So if I redraw this picture in the x coordinates, it's as if I've taken this picture and squished it in, right? And when I squish it in, then I'm going to get a picture more like this. And to calculate the area there, I'd be calculating this integral. The integral from 0 to 3, this is x, of f of what u is equal to in terms of x, du, which is 2x dx. And the whole gimmick here is just that I'm trading the width in this picture for the height in this picture. And the factor that relates the width here, the du's, and the height here, well, that's exactly this factor here, right? That's du, but written in terms of dx.